We're going to start now. We're about 10 minutes late. We'll go on till 11:45. Any questions so far, or shall we go on? Okay, we were talking about martingales. That's where we ended last time. As I may have indicated to you early on, martingales have a colorful history as a name. It's the betting strategy where you win even if your odds are not in your favor, as we discussed last time. You bet 1 rupee, odds against you are 90%, you lose. Then you bet 2 rupees, odds again 90%, you lose. Bet 4 rupees, so on and so forth. When you win, your overall winning will be 1 rupee. Multiply that by a few $1,000,000, not so bad, right? And then martingales itself corresponds to the saddle that a horse has, as we say in Hindi, lagam. It's all about zaban pe lagam dena. It keeps things in balance basically. So it keeps it doesn't let things move around too much. So that's the spirit of things. Okay, so what's a martingale? We defined it last time. A sequence of random variables Mn is called a martingale. First, a regularity condition that these expectations in absolute value of each random variable should be finite, right? And then the main condition is that the conditional expectation, looking in the future, the average change should be 0. Mn plus 1 minus Mn is the change. If you're at time, if you observed M1 to Mn, then the average change should be 0. So expected value of Mn plus 1, given the history so far, should be Mn. You with me on this, right? Yeah. So this is a good way to think about this, but a more general way, which has its merits. So let Fn be a collection of sigma algebra. So we'll introduce the idea of filtration, where Fn is a subset of Fn plus 1. So it's a growing sequence of sigma algebras. And what you're trying to capture is growing information with time. So Fn plus 1 has more information than Fn, right? Let Xn for each n be a random variable. This is Fn measurable, right? So if for each n, Xn is known when Fn information is available, right? That's kind of what we're trying to capture. Then it's an adaptable process. This Xn process is said to be adaptable with respect to filtration. So you think of stock prices at time n, right? So we know them at time n. At time n, we don't know the stock price at time n plus 1. That's still random. But the stock price process is adapted to the time. But in this case, to all the information that's available till time n. All right, so let's carry on. So now so we have a more general definition now of sigma algebras, and you'll see this all the time in the probability that we'll do in continuous time. Be an extension of this. So sequence of random variables Mn is adapted to underlying omega. All the random variables have to be defined on omega. This is important. Huh? There's an underlying sigma algebra. That's a big sigma algebra. All random variables are measurable with respect to that.
So this contains all of my fn's.
That contains all of your fn's. But then you have this filtration Fn, which is increasing. And Mn is going to be adapted to that filtration. And there's a probability measure B.
Fn is in F.
Yeah. Yeah. Each Fn is in F.
And out of all of these fn's, F0 would be my smallest sigma.
Smallest, yeah. Yeah. F0 is what you know when you attended the first lecture of this course. Before that, F is what you know at the end of it. May not be much change from some people, but okay. All right, so this is true, and now we have expected value of Mn plus 1 given Fn. So this is, there should be a subscript here. Given Fn is Mn. That's the definition now. So more general Fn, Fn need not be just M1 to Mn. It could be M1 to Mn and some other X1 to Xn and some other Y1 to Yn. So we allow for all of that. It's all the information that you have at time n. Right? Okay, now let's do an example. So the most basic example is a mean zero random walk. Everyone's kind of heard of what a random walk is, right? At every time you go up and down with probability half. So it's a symmetric random walk, and it's simple symmetric random walk because, so I'll come to that later. Right now, it's not simple. Right now, it's not symmetric or simple. Uh, but in this case, I'm going to assume that each increment of this random walk, xi, is independent, right? And mean zero. Then you can see that, okay, well, let's just see all the conditions. So if we want to show that this Sn now is a martingale, you kind of expect it because every new increment is mean zero increment, independent of everything you've seen so far. So not surprising. So first, technicality, you have to check that, expected value of absolute value of Sn should be finite. And that's not really a big deal, right? You can just apply Jensen's here. It just has to be finite for every n. Now, yeah, right-hand side, for example, is going to infinity, but that's okay. It just has to be finite for every n. All right, so it's a mild technicality. And then this question here, uh, well, E of absolute value of xi is likely to be positive, right? It's absolute value, yeah. Okay, so this guy is Sn plus xn plus 1, Sn plus 1, that's how we define it, right? By linearity, I can separate the two. And E of Sn, given all the information, it's known, I can take it out. So it's just Sn. And this guy is 0 because of independence, given Fn.
Fn is the current field.
Yeah, so I should define here, Fn in this case is sigma x1, x2 through xn. Yeah, smaller sigma algebra, which makes x1, x2 through xn. Take it. Yeah,
Why do you know that expectation mod is?
we've assumed that.
Oh.
Yeah, oh, yeah, that's right. Sorry, I didn't mention this. Yeah. ठीक है. Everybody with me on this? But thanks for pointing that out. And remind me again that your questions are not being heard on the YouTube. So I should repeat them. So the question was that E of absolute value of xi, how do we know it's finite? And the answer is because I said so. Hmm. Okay.
And for this E of xn plus 1 given the filtration till n is equal to 0 because of the martingale property.
No, that's what we just showed here, right? That's the martingale property.
Yeah.
That just followed from here. So this Sn plus 1 is Sn plus xn plus 1. E of Sn given x1 to xn is just Sn,
Yeah.
and this guy is 0. So it becomes Sn. So hence we have the martingale property.
Okay.
We've shown the martingale property. Hence Sn is a martingale.
Wait, we've shown the martingale.
That's right. That's right.
But then why would xn plus 1 given the filtration till n be 0?
Because we've assumed it's independent, right?
Okay.
See, we've said that if the sigma algebra is independent from the random variable, then the conditional expectation is equal to expectation.
Yes.
And the expectation of xi plus 1 is 0.
Okay, that we know from.
That we assume, yeah. ठीक है. Sorry, there are all these typos. I should have corrected them. All these guys here are subscripts. All right, so we'll carry on. Okay, there's one more martingale that's hidden in a mean zero random walk. There are a few more, but let's just talk about one more. Okay. So now I'm assuming that variance of xi sigma square is finite, and I'm assuming variance of xi is independent of I, just to keep my life simple. Right? Then the claim is Sn square minus n sigma square is also a martingale. Right? So I'll have to show E of Sn square minus n sigma square is less than infinity for all n. I'll trust that you'll show this to yourself. Because this is easy enough to show. And then the next part I have to show is that expected value of mn plus 1 given x1 through xn is mn. Right? How do I evaluate that? I'm simply going to open mn plus 1 up. right? Then I'll just open up the square, Sn square, Exn plus 1 square. I've not written the cross term. Why does that not matter? There's a cross term, right? 2 times Sn Xn plus 1.
Sorry. One guy in zero because you have condition on it, so it's good.
Yeah, actually, I should explain it. It's not that obvious. Expected value of Sn Xn plus 1 is equal to expected value of Sn Xn plus 1 given Fn. We know this, right, from Tauber property, right? Expected value of any random variable is expected value of that random variable given F0, the trivial sigma algebra. Then we apply the Tauber property. Now you see here that this is equal to expected value of Sn and then expected value of Xn plus 1 given Fn. Right? And now, how does the result follow?
Zero.
This guy here is 0.
EFX.
This is 0. So then the cross term is 0. So this you should be aware of, this argument. Okay. Once we have this, then why does this equal to Mn? Anyone? It's known given x1 through xn. Right? It's a known variable, so it just comes up. It's a function of x1 through xn. It's sigma, it's measurable with respect to sigma x1 through xn. So we already said that what is known just comes out as a random variable. It's like you observe something and then your conditional probabilities. And so if something which is a function of these observed things is just known. All right, now can you complete the argument for me?
So the E of x square n plus 1 minus sigma square
Hmm.
is equal.
Why is that the case? Why is E of xn plus 1?
That's just your
square.
variance, no? There's a second.
That's
moment.
the second moment,
Yeah.
and the first moment is 0.
Yeah.
Right? First moment is 0. Okay. So we get this, Mn. All right. So even in this, I indicated earlier that martingales are powerful because, we saw this martingale convergence theorem. Just out of the blue, you get almost sure convergence with a very simple condition. So we'll see a little bit more of that, but not all of it. There's lots that one can do with martingales. We'll just see some of that right now. But martingales are going to be inherent to stochastic integrals. So we've just gotten started to use them. Okay, other example is a product martingale, as we discussed earlier on as well. So this is product of xi, I equal to 1 to n. All the xi's are non-negative and they're independent and they're mean 1. Right? So is it clear that this should be a martingale? Huh?
So
Multiplication is always annoying with expectation, but I think Tower property should have.
Yeah. So this, of course, you agree it's all non-negative, so it's just the individual terms. Not quite sure I put absolute value everywhere, but no harm. And that's going to be finite. Okay, Emn plus 1 given Fn, that's the main property. So Mn xn plus 1 given Fn. Mn comes outside, it's known. E of xn plus 1 given Fn by independence is just E of xn plus 1, and that's 1. So you get that's a martingale. So this is going to be incredibly important. The whole of Karznauv's theorem, stochastic calculus, is based on the fact that these things are martingales. We'll see what Karznauv's theorem is. Sorry?
Mn came out as expectation of that, but expectation of Mn given Fn is just Mn.
Yeah.
That's what we do.
Yeah.
And then expectation of xn plus 1 given Fn is xn plus 1, so this is independent of the other variables, and Fn is defined as a small Fn contains.
Yeah. In any
So
case,
we need to write about that now.
xn plus 1 is independent of Fn. That's right.
That is because Fn is defined as a signal level
That's
containing x1 or
That's right. That's
So
right.
when we write it in exam, you want us to argue.
That's right. Yeah. I mean, you're not giving marks to me, so it's okay.
I just wanted to.
Sure, sure. No, that's.
The argument.
I mean, what you really need is for all this to work is that each xn is Fn measurable and xn plus 1 is independent of Fn. Whatever the Fn be, it need not be sigma x1 to xn. It can be bigger than that. But these are properties you need.
But this is, how do we know this here? That's another question.
No, you need this.
If we need this, so how did we know that that's true here?
I just told you that, right?
No, so that's because we constructed Fn to be like the sigma algebra containing that sort.
No, all I'm saying is if I tell you that that each xn has this property, that each xn is Fn measurable, right? It's a Fn is a filtration, and xn plus 1 is independent of Fn.
No, but I'm saying let's just look at this example. Mn is defined as a sequence of random variables.
Yeah.
And I just have some facts on expectation. Oh, you're saying put that in the premise as well.
Yeah, that's what I say, yeah.
Oh, you're just saying put that in the premise.
So when I say I told you so, I mean it's right here in the premise. So it's true that I didn't write it here earlier. I didn't want to kind of overcrowd the thing, but yeah, it has to be there. I mean, I told you that they're independent, but I could be more clear and say, okay, xn plus 1 is independent of Fn. Yeah.
One question.
I mean, it's kind of implicit in my discussion that I'm taking Fn to be sigma x1 to xn. So then when I say they're independent, sure. Yeah.
One question. So, assuming Xn is measurable on Fn and Xn plus one is independent of Fn,
Mhm.
then let's say I take any general binary operator
Mhm.
on xi and xj,
Mhm.
and then I define mn as the since I'm like this is summation or the multiplication of I define it in such a way,
Mhm.
and then the expectation I define is just the identity of it.
Mhm.
So would it hold in general?
No, of course not. And why don't you construct like 200 examples where this will not work? Yeah, I mean, this is a very special structure, right? That's making everything work.
This I don't know where is, but so the intuition is in Excel, it is like we can't fit Excel plus one. Like by fit I mean like the
Intuition is very
not
simple.
considered.
Intuition is Fn is all the information available from x1 to xn. That tells you nothing about xn plus 1.
Okay.
So x1 is independent of that information. So its probability distribution, its expectation does not change.
So the sigma algebra is the information you have available.
That's right. That's a way to
That's the
that's a way to intuitive way of thinking about this thing. Okay. But otherwise, you have to kind of go back to the definition of independence that we discussed. All right. Shall we carry on? Any questions? Yeah, so I've been a little cavalier in some of these writings. This shows up again. All right. Maybe I did not discuss this last time. Maybe I kind of just discussed this very quickly. But let me discuss this again. So if Fn is a martingale, now we know what a martingale is. And when I say a martingale, I'm implicitly assuming underlying probability space, a filtration, all that, right? Such that sup and E of Mn is finite. See, E of absolute value of Mn has to be finite for each n. But if the sup also is finite, right, and which is not a trivial condition to assume, typically it will increase. Right, for IID variables, when you sum them up, it typically is going to increase.
If it's non-decreasing, then it must just be.
No, I mean, non-decreasing doesn't mean increase, infinite, right?
Yeah.
Right? Any non-decreasing sequence can be finite.
Yeah.
Then there exists a M infinity. I mean, this is kind of, in real analysis, I give you a sequence, non-decreasing sequence, whose sup is finite. Then the sequence is converging to a number. So this is kind of a very nice abstraction of that idea. Yeah?
So, it's an infinity.
Right.
The random variable. What is it? Is it F measurable, the F that
Yeah.
we initially?
That's right.
So is it the case that if I took, say, F and F prime, and both contain, then this theorem will give me an M infinity for this and an M infinity? Right? Does the ultimate filtration that you're taking on the top change the M infinity that you're taking?
No.
So this is unique in a precise.
I mean, the way it's going to work is, so each Fn is increasing. And to define M infinity, you look at union NFN
And the smallest sigma.
and the smallest sigma algebra that contains
Right.
this. And that's your F infinity. And you can argue that F infinity is contained in F. But But then, yeah, there's no more information. All the bigger algebras will have the same random variable, right? But what's nice is when you say sequential non-decreasing, then there's a limit that exists and you converge to it. You can say that about random variables in this setup. All right. So one more martingale, which is very interesting, called Doobe's martingale. All of the work on martingale theory was done by Doobe. So he kind of cleaned up all these things. He defined martingales. He proved most of the interesting results.
You're not proving.
This will prove. It's easy enough. No, that will not prove it. Yeah, I mean, that theorem takes a while to prove. It's perhaps one of the more beautiful theorems you'll see, especially the proof and all. It's a nice proof. I'll encourage you to see it on your own. But this would be proved in an advanced probability course, not in a stochastic calculus course. But yeah, it's not that difficult, but it's just very elegant. Yeah. And the reference for that is David Williams, if you want to read that book, Probability and Martingales. It has a small chapter, 3 pages, which does this proof. David Williams. Probability and Martingales. It's generally a good book to have. Okay, so Doobe's martingale. So X is a random variable on. Yeah. Now X is just a random variable. Huh? It's not a sequence of random variables. It's just a random variable. It has finite expectation. There's a filtration underlying. So Yn is E of X given Fn. Right? My projection of X on the space Fn. My best guess for X given the information Fn. There's a variety of ways of thinking about this. So this is a sequence of conditional expectation. E of X given F1, E of X given F2, E of X given F3, and so on. That sequence is a martingale. My best guess is I get more information, on average does not change. There was no signal in it when I made my guess at some point. It was all noise. So let me just try to make this precise. First, now we didn't quite do this conditional Jensen's. Conditional Jensen's is f phi of E of X given phi is less than equal to E of phi of X given phi. Again, almost surely. This is conditional Jensen's. I won't prove it. Phi is convex. Yeah. Thanks. Phi is convex. Right. So this conditional Jensen's hold. Again, I'm not kind of prove all the conditions under which it holds. That takes time. We're avoiding that. But you need moment conditions so that everything should be well defined. Yeah, so now that we know this, now phi is mod of X is a convex function, right? Oh, sorry. So mod of X is a convex function. So it's, yeah. So basically what I'm saying is, yeah, this is one more beyond Jensen's. This mod here is less than or equal to this quantity here, both inside the expectation. So both these random variables have this inequality, and now I take expectations on both sides. So let me just spell this out more. E of X given phi is less than or equal to E of X given phi. This is by Jensen's. And now I take expected value on both sides. That's what I've done here. And expected value of this guy is just equal to E of X right here. That's finite. And hence expected value of this guy is also finite. We want to show that expected value of absolute value of Yn is finite, right? So that's finite because it's dominated by this E of X. Is this clear to everybody what's going on? No? Yeah, no, it's just kind of too much notation.
Not
No.
sure I understand conditional. Yes.
No, I just want to show that, okay, that I'll come to in a moment. We just want to show this for all n. to show that this guy is a martingale. This is a condition that we need to show. And what we've shown is that this quantity here is bounded from above by this quantity right here by conditional
So
Jensen's.
first we showed that mod of expectation of x given f naught is bounded above by expectation of mod of x given f. That came by conditional Jensen's.
That's right.
Then because LHS is less than equal to RHS, expect x.
We do expectation on both sides.
will keep it.
That's right.
So, okay, that's how.
That's how it went, yeah.
Yeah.
Okay, and then we found that, okay, the right-hand side is a uniform bound. It's independent of n. Is this clear? Yeah, no, let me just do it separately. I see a lot of, see, what do we want to show? We want to show this. Right? This is a yn right here. We want to show expected value of absolute value of yn is finite. Jensen's tells me that phi of E of x given phi n is less than or equal to E of phi of x given phi n. Phi is convex.
Mod is convex.
This implies that absolute value of E of x given phi n is less than or equal to E of absolute value of x given phi n. Right? Because the absolute value of x is a convex function. No, you're right. That's a typo here. Thanks. Yeah.
Now, the condition on measurability.
I mean, E of x given Fn is Fn measurable, right? E of x given Fn is Fn measurable. This, whatever, so I don't need any condition on x. On phi. Phi is just a convex function. Phi is just a convex function. It's a convex function, a Borel function, so don't need to worry about
I
that.
mean, if x is measurable, then f of x is also measurable.
Yeah, because f is a Borel measurable function. Yeah. So that's what we covered last time. So, continue, yeah, convex functions will also be. Again, we've not shown this. I mean, we've not shown that convex function. Well, yeah, we've not right now argued that convex functions are Borel measurable functions. It's an easy argument, but we've not done that. All right. Sorry, I'll have to jump on some steps in these things. I can't do each and every step here. Yeah, but convexity need not imply continuity. You can have discontinuities at the boundary of the support. So you need to do a little bit more work. Okay, so then we got this. So far you're with me on this? And now I'll take expected value of this and expected value of this guy here. And this guy is just expected value of x, which you're given is finite. All right. So you with us so far? Okay, good. So that tells me that this property at least is true. Actually, I have something extra. Do you see this? In this case, I have something extra. Because each expectation is bounded from above by a same constant. So supremum is also bounded above. Right? So that's something extra that I get here. Everybody with me on this?
Like, how does boundedness of expectation apply?
No, but we haven't shown that if x, we haven't shown that x is bounded up, but that expectation of x given f will also be bounded up.
Yeah.
Do we need that here? I mean, it's true, but we don't need that here, right?
Yeah, they just calculate but down. No, how you should we soup things?
You were seeing everything on the phone?
Yeah.
It's a grand entry, yeah.
Expectation by n.
Yeah. All right.
Yeah.
Good.
But I still didn't get how does this imply?
See, this guy here is yn.
Yeah.
So we have shown that E of absolute value of yn is less than E of x.
Yes.
for all n. So I can take supreme on the left-hand side. See, if I give you a bunch of numbers, all of them are bounded by some number, then the smallest upper bound to those guys will also be bounded by that number.
Okay.
Right?
Okay.
Because it's the upper bound to all these guys, right? So it's bigger than the smallest upper bound to all these guys.
So we say the supernova distance is finite.
Yeah. So we can use the martingale convergence theorem. Okay, but we still have to show the main property, right? And this is where I've been lax with these slides. The tower property will help us. So we have to show that E of yn plus 1 given Fn is equal to yn. That's what makes it a martingale. That needs to be shown. And why is that true? So that's same as this quantity right here. And then
X is independent of Fn plus one.
x is not independent of Fn plus 1. You're still on the last slide.
This will just be yn.
Hmm?
X given, yeah, X given Fn plus one is just y plus one.
E of x given Fn plus 1 is yn plus 1.
Yeah.
See what again?
N is contained in Fn plus one.
Yeah.
That's why. Fn is
Yeah,
contained in
that's
Fn plus
right.
one.
That's right. That's right. So, by the way, is everybody with me so far? What are we trying to show? I've given you an arbitrary random variable. It's like,
X given Fn plus one should be y plus one.
X given Fn plus one and we will y.
this is my yn. I'm trying to argue that yn is the process yn is a martingale. So yn is Fn measurable by definition. Expected value of absolute value of yn is finite. We just showed that. Now we have to show this property. E of yn plus 1 given Fn is equal to yn. We need to show this, right? For this to be a martingale. But then we realize that yn plus 1 is nothing but E of x given Fn plus 1. And then we are looking at this conditional expectation of this conditional expectation given Fn. Fn is a smaller sigma algebra. So we just argued earlier that this will be E of x given Fn by tower property. And that's defined to be yn. Okay, so all with me on this, that this is indeed a martingale. I'm trying to interpret this, I forget now, but think of x as some parameter you're estimating from data. And x1 through xn, you like in economics, x1 to xn, you got that much of data. And with that, you come up with an estimator for the parameter. The more data you get, the better your estimator is. Right. But the future guess that you have, yn plus 1 given Fn, is just yn. At least on an average, you don't expect to learn anything, any signal. On an average, you expect to be the same. Because if there was a signal, then you would have adjusted your guess already. Why would you accept a guess which is missing out of the signal? So yes, that's kind of the intuitive feel for this. Okay. And now we have that yn is E of x given Fn, and that converges to y infinity by martingale convergence theorem. We'll see if we need to discuss this further. I mean, this comes up a lot, but we may not need it in this course. So we'll see.
What interpret this yn? What is yn?
I mean, it's your best guess for x when you have all the information, x1, x2 through x infinity. Right? It could be that when you know x1, x2 through x infinity, then you know x exactly. Then you have to argue that if your x was f infinity measurable, then this will converge to x. E of x given Fn will actually converge to x. But it may not. If X is not F infinity measurable, if it's outside that, then it converges to your best guess given all the information.
Because you're limited by the information.
That's right. That's right. Yeah.
By finite.
Is Y infinity finite? It's a random variable. Yeah, it's a finite random variable. Sure. I mean, all these are in a sense that, one can argue, which I've not done here, that expected value of Y infinity is less than infinity. Just like expected value of X given Fn was less than infinity. You'll get this, and those of you who know Fatu's lemma will see this, should see this immediately. It actually gets used. But because it's a finite random variable, because it has a finite expectation, it cannot be an infinite random variable.
No, I know, like, just.
How much do you know Fatu's lemma?
It's just that expectation of one where less than equal to like swap limits and so limits and expectation.
See, what I've not done is, I've not told you what Fatu's lemma is. But Fatu was a big Fatu. And the, and the lemma is E of
Expectation of limit one guy.
lim inf, this is lim inf, one notation, and goes to infinity. Xn is less than or equal to lim inf and goes to infinity. E of Xn. Now this is less than or equal to sup n E of Xn. Lim inf will be less than or equal to sup, right? That is easy to accept. So now can you prove the result? Prove that the Y infinity that I mentioned to you earlier is actually its finite expectation.
Yeah, we already know that this.
Because the limit exists.
So it must be.
Lim inf is equal to limit. This is limit is equal to limit.
Limit exists because MCD.
Limit exists because of MCT. MCT now defined as Martingale convergence theorem. Yeah. ठीक है. So this limit exists because of the big theorem, right? Now the question is, you want to argue that E of Y infinity is less than infinity, and you argue that this is less than or equal to this guy right here. All these are again details which I didn't want to spend too much time, but it's probably good to spend some time. Yeah. All right, shall we carry on? I talk to the camera as if there are a lot of people who are listening, but there's some guy SA, I guess. Otherwise, I can, without you're here, right? Okay. Okay, so let's carry on. Shall we carry on? Is that okay? So now what we'll do is we'll use martingales to make more martingales. Right? Given martingale to construct more martingales. And it's kind of, we'll see this a lot. This happens a great deal in stochastic integrals. Through stochastic integrals, which are martingales, often we'll see them. We can construct new stochastic integrals, which are also martingales. So this gives you a feel for what's going on. So we are given a martingale Mn. So we construct another martingales. First, we need the idea of predictability. So adaptability was if a random variable Mn is known when Fn is known, if it's Fn measurable for each n. We'll say the sequence of random variables Cn is predictable if Cn is Fn minus 1 measurable. If I know n minus 1 information, then I know Cn. And
It's predictable always with respect to one thing.
yeah, the whole sequence is predictable. And what we are trying to capture is you've seen your winnings in a gambling game. See, random walk, one way to think about this, it's like winnings in a gambling game, which is fair. So on average, you're neither winning nor losing, right? Very unrealistic, but nonetheless, that's a good model of a fair game, right? Now, suppose you observe your winnings up to n minus 1, and then you decide your strategy, how much you're going to bet. So what you decide is a function of everything up till n minus 1, right? So in that sense, this betting process is a predictable process. It's not an adaptable process. You don't see the outcome and then decide how much to bet, right? At least not the retail investor in the world of finance. If you have inside information, then you can see the observation and decide how much to bet. So those issues do happen. Okay. So now everybody is with me on this predictable process, right? It's sequence of random variables C1, C2, C3, so on. Each Cn is Fn minus 1 measurable. I know it when I know all the information till Fn minus 1. Right? Now the claim is that if I construct.
That's M subscript K minus one, right?
Yeah, no, that's true. I was supposed to correct all this. I've not done that. Yeah. So you see a bit of that happening in these slides. Yeah.
And starts at 0.
N starts at
6.
0. Sure. Yeah.
So Cn would start at 1
Yeah.
because
True.
C0 is not.
C0 would not make sense. Absolutely. That's a good question. Yeah. So we'll start with M0. M0 is C. Often we take M0 to be 0, but it doesn't really change anything. And Cn, we'll start with C1 basically. Right? Yeah. So I've not been careful. Okay, and the point is now, Mk minus 1 is my winning in the kth experiment, in the kth K. It's a zero mean winning, right? And Ck is the bet I made after observing data till K minus 1. So I observe that data, I make a bet Ck, and I have a winning Mk minus Mk minus 1. And now I'm just collecting the total amount that I won. That's my new martingale Yn. In n steps, how much have I won? So is this clear?
So on an average, you're winning nothing.
On an average, you're winning nothing. Yeah. So we'll prove a big theorem. Not only are you not, if you were to play in a fair game, if you decide to stop after 10,000 games or 500 games or whenever it's midnight, you've not made anything on average. You've not lost anything on average, more importantly. But even if you were clever and you said, okay, I'll stop like we often go. I'll stop when I lose so much, or I'll stop when I win so much. Even with those kind of strategies, which are random, you don't win anything. On average, you don't win anything. So that's a powerful result. Expected value of a martingale stopped at a particular time is also M0. It's not changed. So when is that true? When is that not true? We'll discuss that in the remaining part of the lecture. But that's another big result, martingale stopping time theorem. Okay, now I need some technicalities, some technical conditions to make life easy. So I'll assume that all my C and the bets that I'm placing are bounded uniformly by K. That makes the analysis much simpler. Right? Once I assume that,
Cn being finite, being uniformly bounded
yeah.
is like needed.
I mean, it helps. It makes things easy. Your question is, can I not have this and still have martingales?
Yeah.
Yes.
No, but without having this, whatever you said is a sufficient condition? Or do you need some to say that Cn is not is finite? Is that enough?
Okay, let me just say what I'm trying. My big comment is Yn will then be a martingale.
Yeah.
So Yn is a martingale when the Cn's are uniformly bounded.
Only when few.
No, so that's not what I'm saying.
So my point is the Cns are what's like the weakest condition that you need?
Weakest, so I can tell you, not the weakest, but if the second moment is bounded, that's enough.
Just bound.
If they're L2, that's fine. Yeah. Right.
For
Because,
Cn.
for Cn. Because what I can use is I can just, and I need M's also to be in L2, in the sense that I can just apply Cauchy-Schwarz to this. Right? I can bound each term here by expected value of Ck square and expected value of Mk minus 1 square. If those terms are finite, then this term is finite. If each of these terms is finite, then the sum is also finite. Those are easy things to show. So a good weak condition is that these are L2 bounded. Right? Now, can you go more? Yes, but then you're nitpicking. For us, for our purposes, that suffices.
So small.
Small c, no significant. I mean, M0 has to have some value. I could also keep M0 to be random. Yeah. Okay, so I have to show that this transform is a martingale. So I was started with one martingale, Mn, and I came up with a new martingale, Yn. Now, there's nothing to stop you to use this yn and come up with another martingale cn and do this process ad infinitum. So all these things are done with stochastic integrals. It's quite common to do these things. Okay, but let's prove this part at least. This proof is not so hard, so I can prove this. So first I have to show that expected value of absolute value of yn is finite, right? That just means this quantity right here. And I can apply Jensen's and take the absolute value inside the expectation. Okay. Right, Ck is bounded by k, so I can take that out. But as you can see, all I need was this expectation of the cross product is finite. So conditions which ensure that will work. All right. So this k you can take out. This mk minus 1 I can upper bound by, in absolute value I can upper bound by absolute value of mk plus absolute value of mk minus 1. And all of these are finite because we have a martingale. So I'm not asking for much and hence I'm not showing much. Right? It's a kind of being generous in the proof. So far so good?
From the integrativity part of it.
Yeah.
Now show that.
The main part.
Yeah,
That
that
the-
also.
But the new term that's added, the increment is mean zero. Go ahead. That's right. Yeah. Which is not so interesting here, but it becomes more interesting in the stochastic calculus setting. Yeah. But go ahead. So now we have to show the main property, martingale property, right? On an average, things are not changing. So really what we have to show is that the increment of the martingale, yn minus 1, its conditional expectation given fn minus 1 is 0. That is the martingale property, right? And this yn minus 1 is just this quantity right here, cn into mn minus 1. That's exactly the bets I was making. And you can see that's very important that cn be, that we be able to take cn outside here. It doesn't depend upon mn minus 1. So given fn minus 1, I know cn. That comes outside. And now what's remaining here is 0 mean. Right? So in this martingale transform, I'm just adding extra noise each time, whose conditional expectation is 0. Okay, so hence I conclude. Everybody with me on this so far?
But when you're just adding CN into amendment, which is mean,
Yeah.
means amendment.
Well,
Let's do the definition of pi.
let's do that.
See, this is CK FQRS. This is M subscript.
Yeah, no, this is all.
Okay.
So by the end, you'll just have CK and K minus NK. And everything else will just cancel
Yeah.
out and add this one.
But again, the intuition is this is the martingale increment. This is the winning from the kth game. And CK is the bet you placed. The bet was placed before the kth game was played. Yeah. What's that? Still, it continues to be a fair game. Yeah. Right. Any questions so far? Shall we go on? All right, we said this already. By the way, at this point, we should kind of emphasize this is the martingale property, right? And now I can take expectation on both sides. So the unconditional expectation of the martingale terms is also equal, all the terms. Right?
When probably that's the case,
Mhm.
that for the martingale conversion theorem, you want that the expectation, the supreme of the expectation, that's okay. When you take supreme of it might still be fine. No, okay. But when you take the supremum of yn, that's mod, is that the problem? Mod is the problem.
What is the problem? Yes.
So the variance might be increasing as the martingales go up and the mean remains the same. So when you take mod, they.
That's right, yeah, yeah. Yeah, so it's something special has to happen for the supremum to be finite.
Not just that, but if you take expectation of mod of Mn is n, which is it is the closer ten. No, say that expectation of mod of Mn is n. Yeah, then you go, yeah.
Then you're in trouble.
It's still a martingale.
Yeah, but the soup and his point is supremum is not satisfied.
Exactly.
Yeah, yeah. So, ठीक है, so what else does one want to say here? Yeah. Yeah, let's carry on, I guess. Nothing else.
You were saying that the expectations are.
Yeah, expectations are the same. So I was wondering if there's anything more to be said. I think the other thing one can kind of say here is that, okay, let's do E of Mn plus 1 given Fn minus 1. What do you think that's equal to?
Minus.
Still be Mn minus 1, right? Yeah.
Because Mn plus one.
Because
And then is by martingale, but whatever is Mn plus one.
Wait, can one show that this is just equal to N zero?
Hmm?
Can one show that this is?
no, it's not equal to M0. It's not equal to M0.
Mn plus one minus Mn plus given Mn given Fn minus one.
Yeah, I mean, so say again.
It doesn't work out. You write this as Mn plus one minus Mn plus Mn given that.
No,
And
no.
one guy comes out as.
No. Not really.
I see it.
It's true that you want to somehow get Mn out of it because we understand Mn. Mn is we can play with Mn. But the way to do this is, I'll just answer it because I can ask you to guess, but it might take some time. I can use a tower, but in what way will I use a tower property? Excellent. Yeah.
But then that gives you only almost short equality. So all of this equals to is almost short. So I think in general, the expectation is just almost short.
See, the point is, conditional expectation of Mn plus 1 is same as conditional expectation of Mn plus 1 given Fn. Sorry. Right?
Yes.
And now what's conditional expectation of Mn plus 1 given Fn? That's Mn. This becomes equal to E of Mn given Fn minus 1.
Why is Mn plus one expectation of Mn? Why could you replace Mn plus one with expectation of tower property, right?
This is the tower property, right? That's the main tower property.
Because Fn minus one is smaller than Fn. Okay.
Yeah. And this, of course, is equal to right. So is this clear? Yeah, Mn plus 1 has the same expectation as Mn plus 1 given Fn. Okay. Mn plus 1 has same conditional expectation as Mn plus 1 given Fn.
I think we showed at the start of the course that E of Mn plus K given the course that is equal to.
Yeah, so that now from this you can write that E of Mn plus K, let's call it.
We did that in the start without this filtration stuff. That was with the.
That's we kind of stated it, right? Yeah,
We did exactly this without the.
that's right.
Given M1, M2.
That's right. Yeah. But this was in the discrete setting. Yeah, we wanted to use it, so we kind of just stated it. All right, so this result follows now, right, by induction. Okay, everybody with me on this? Okay. Okay, now let's have this idea of a stopping time. So Sn is again now it's a simple and symmetric random walk. Symmetric because x takes symmetric values, +1 and -1, with probability half. Simple because it takes values +1 and -1, so it's simple random walk. Symmetric because the probabilities are half-half. That's the right terminology. All right. Okay, now let tau be the first time Sn is equal to +1. This tau is a random variable that's called a stopping time. Have you heard this term before, stopping time? Many of you have not heard this term, right? You have, or, huh? Okay, yeah. You're using that tradition saying yes. Okay. All right. So stopping time is, let's just talk about that for a moment. So tau will be a random variable, and suppose omega such that tau omega is less than or equal to n. So tau is a integer valued random variable, whole number basically. And if tau omega less than or equal to n, if we collect all the omegas where tau omega is less than or equal to n, if that is Fn measurable, so when I've seen all the information till Fn, I know whether tau is less than or equal to n or more than n. I know whether I should have stopped or not stopped. Right? Those random variables are called stopping times. It's a little complicated idea. What you're trying to capture is quite simple. So this is the case. I stop when my Sn becomes equal to +1. Okay. So now let's look at the time tau less than or equal to 5. So if I observe x1, x2, x3, x4, x5, I can decide whether Sn S5 has become equal to 1 or not. Right? So this is an example of stopping time. This is bothering. I'm just going to erase it from here. So let's talk a bit more about stopping times.
What is this? Stop.
What's that? Yeah, anything with this property is called a stopping time. Yeah. So I define first a random variable tau, which takes non-negative integer values. Now, whenever I look at tau omega less than or equal to n, right? If this is Fn measurable, in our case, in this world, we are looking at Fn to be, it can be bigger than this, but let's take this as kind of a prototypical. All the information based on x1 to xn. So if tau omega less than or equal to n depends upon x1 to xn, if I by observing x1 to xn, I know whether tau is less than or equal to n or not, then my tau is a stopping time. If that has to be true for each and every n. Right? So tau less than or equal to 26. Can I observe x1, x2 to x26 and decide whether tau is less than or equal to 26 or not? Right? Tau is the first time I hit +1. So I observe x1, I observe x2, I observe x3. So I've observed s1, s2, s3, s4, x26. Right? Based on that, I can figure out whether any of these guys have crossed +1 or not. If they've crossed +1, then this tau that I've defined is less than or equal to 26. If they've not crossed this, then tau is bigger than 26. Right? So I know this, I know whether tau is less than or equal to 26 based on information f of 26. I know the tau is less than or equal to 5 based on information f of 5. So for every n, I know this. So this is an example of stopping time. Intuitively, when do I stop? I stop when my random walk hits +1. For that decision, I don't need to see the future. If I stop at time tau equal to 30, it's just a function of everything till 30, x1 to x30. I don't need to know x31 for it. So those are examples of stopping times,
Something.
which is not a stopping time. Yeah. So that should be, suppose I'm going to observe the tau is equal to supremum n less than or equal to 100, such that Sn is equal to +1. Last time in 100 steps, I hit +1. See, if I tell you tau is 88, then I need to know what happened at S89, S90, S91 to conclude that thereafter I did not hit +1. So I need to look in the future, right? So it's like, when is the toast done? You wait for it to become dark brown and stop 30 seconds before that. Now that's not a stopping time because you have to look in the future for it. So wherever you don't need to look in the future, that's called a stopping time. So all our betting strategies hopefully don't involve looking in the future. So those become stopping times.
So that set of omega is fixed for
Set of omegas,
that set. In that definition, tau will be a random.
you mean this omega or what do you mean?
So,
So what that set should be in. Yeah, that's what fixed, it just saying that this set is a convention.
so what is that definition? Tau will be a random variable.
And that definition is just like, the tau is random. Or a bar, or yeah.
No, hold on. This is come on, it's a respectable definition. What do you mean?
So there is one definition that tau is a random variable and then this is an
Yeah.
imaginable. But we're not defining this concept.
No, I've written it wrongly.
I mean, that
Is it that the tau is the stopping time?
No,
if
no,
the
no,
tau
it's-
is an argument that-
Yeah, I know. Tau will be a random variable. No, this is just my typo here. So let me just write it. Tau will be a random variable if tau takes integer value and so this is a definition, right? It's and here and omega. Yeah, so this is so that tau omega less than or equal to n. This set I have to collect. Now I've not made a big deal out of it. No, I have actually, yeah. So this set should be measurable and it should belong to Fn for all n.
and then this tau will be stopping time.
Then it's called a stopping time. Yeah. So I should. Tau will be renewable, and this is true. Then it's a stopping time.
You also want negative.
Yeah. So if tau takes integer values, yeah, non-negative integer values, I guess. I'll have to fix all this for your before putting all this on this website. ठीक है, is the idea clear? Yeah, this is wrongly written. Yeah. So now it's unambiguous. And what we are trying to capture is also clear. Sorry, I didn't get a chance to go through my notes last night. It's a mistake on my part. That's the time to fix all this. What's really happened is I gave some lecture somewhere, somebody handwritten the notes. What I gave in the lecture and what was handwritten, there was a gap. But the LaTeX, which took all this, took it from the handwritten notes. So LaTeX has some bugs here and there, which need to be fixed, and I just didn't do that this time. All right. So it's not like I wrote these wrong things. There was just intermediate steps in between. All right, so now we can define a stopped process. So this is a martingale process, but we stop it at a stopping time, right? So let's again this is a subscript here. So this is your martingale transform. It's again a martingale. And now let's take Cn to be indicator that tau is greater than or equal to n. So Cn is a bet I'm making of 1 rupee, and I'm making it up till some stopping time. If tau is bigger than n, then I make a bet of 1 rupee. If tau is bigger than I do, as soon as n becomes equal to tau, I stop. As soon as n exceeds tau, I stop betting. Right? So now the question is, so what's the first question, by the way? Huh? What's that? Is it still a martingale? So what do I need to show for it to be a martingale? Huh?
So we know moment is bounded easily.
Yeah.
This example.
Cn is just 1, right?
Yeah, so you just want to now show that The martingale property holds.
That's right. So what did we assume about Cn, which would make the martingale property hold?
It's,
Predictable, predictable. So I need to show that. I need to show that I,
wait, so Cn is the same Ck here.
yeah. That's it for a given n.
What is tau?
Tau is the stopping time. Yeah.
Arbitrary tau.
Some stopping time. Some arbitrary stopping time. Okay. So I need to argue that this indicator that tau is greater than or equal to n, that's my Cn, is predictable. Why is it predictable? I should know, huh?
I mean, because you know the complement is Fn.
Oh, that's
minus
good.
one.
You see, yeah,
So the complement of this is Fn minus one measurable.
that's right.
So that also means.
Yeah, so tau greater than or equal to n, the complement is tau less than or equal to n minus 1. And tau less than or equal to n minus 1, I know from observing all the information till Fn minus 1. It's a stopping time, so it's Fn minus 1 measurable. Tau is a stopping time, right? So tau less than or equal to n is in Fn, tau less than or equal to Fn minus 1, tau less than or equal to n minus 1 is Fn minus 1.
Just to be very pedantic.
Yeah.
We want that then it should be strict tau greater than it.
No,
Because then it's integers here.
the complement is strict less than.
Yeah, but we don't want strictness and we want.
No, we want
Don't you
less
get-
than because that would be less than equal n minus.
Yeah.
See, complement is tau less than or equal to
Yeah.
n minus
Should
1.
be less than.
Less than or equal to n minus 1. And this, because tau is a stopping time, belongs to Fn minus 1. Okay. So,
I want to-
Hmm.
What is y, what is that notation? Y is equal to mn intersection power.
yes, I will come to that in a moment, right?
That's okay.
Yeah. It's okay for you to look at the phone and know what I'm going to say, but you can't say something that I've not said.
I think I sort of got distracted. by that.
You're violating the stopping time property. In looking in the future, huh? Okay. All right. So the point is, first you have to argue that then indeed this yn here is m of n minimum tau. So that can you see?
Hey, minimum of n and tau.
Minimum of n and tau. Yeah.
It will stop, it will be this.
So I mean, look at this. Either you're on this omega, let's look at it on a particular omega. Suppose tau omega is bigger than n. Then all these Cn's are 1. Then this yn is equal to
That's just n.
just mn, right? And if tau omega is less than or equal to n, then somewhere your Ck is as soon as you hit tau, it stopped. You stop betting. So then this is equal to m tau,
Yeah.
right? So this yn is equal to it's it's m observed at either n or tau, whichever is minimum. Is this kind of clear to people here?
What did you say? N tau? Like after a point, I did not get that. So the summation will be equals to, sir, N tau.
N tau.
N into MK minus.
No, I said on the set where tau is bigger than n, yn is equal to mn. On a set where tau is less than or equal to n, yn is equal to m tau. Because you stop betting, right? As soon as you hit tau, thereafter you stop betting.
Yeah.
So you observed m tau and that's it.
Yeah.
Then it just it stopped after that time. So it's a stop process.
We're missing the minus m naught there somewhere. We should have minus m naught. Because y and by definition, everything is C
Yeah,
is one,
yeah,
everything
yeah.
cancel out, but m zero will win.
That's it, that's it. So this is, yeah.
Nothing will be good.
No, that's right. That's yeah, right. So yeah, no, these are blanks I'm hoping you guys will fill. So yeah, M0 is
It's
here.
wonderful.
Yeah, no. Deliberately planted. right? So it's true. This is, more generally, it's just this. It's this minus M0. Okay. All right. So far, so good. So now we know what a stop process is, right? And we know, more importantly, we know the stop process is a martingale with respect to filtration Fn. Because Yn is a martingale with respect to filtration Fn.
This is a proof in itself. Okay. This is-
M and min tau is a, yeah, this is a proof that stop process is a martingale. We know that now. So now let's have some fun with that. So let's look at tau is the first time that my simple symmetric random walk equals either A or equals minus B. So think of a random walk that starts at time 0. So let me just make that clear before somebody tells me. Right? Yeah. What's that?
Stopping.
Yeah, but we're not discussing that right now. I mean, I'm just defining that one stopping time to whether you hit this or that. So I could have called that, you're right, I could have said either tau A and then tau minus B and then minimum of tau A, tau minus B. Sure. True. Okay, S0 is 0. Tau is the first time I either hit A or minus B. You can see this is a stopping time. Tau less than equal to 25. I observe X1, S1 through S25. I know whether I've stopped or not. Okay. It's a little kind of, uncomfortable definition. Why should stopping time be defined in this manner? You again expect it to be defined more simply. But this is what works. All right. So far, so good. Now, let's look at the stop process. So we want to find the probability that when we stop at A and not at B. What do you think this probability is going to be? Everything is nice and symmetric. Can you guess? Huh?
I mean,
What if A is 10 and B is minus 100?
Yeah, like A over A minus B.
I think my guess is distance divided by distance.
Yeah, distance divided by distances. So now let's make your idea more concrete. So what will this probability be? One distance is A, other distance is B.
A by A.
A plus.
Huh?
A by A plus.
Why do you think I'm kind of like going on and on about this?
Yeah, plus. Good, plus.
Well, something is not good about this answer, right? So suppose A is equal to 1. B is equal to 100. Which event should be more likely?
A. Oh,
Right?
A more.
A should be.
more like.
And what is A upon A plus B?
Oh, great. Yeah. But.
Yeah. So what do you think the answer should be? Yeah, go ahead.
B divided by A.
Yeah.
So, as that index value hit A or B.
Yeah, A or minus B. Yeah. And then you either hit level A or you hit level minus B. So what's the chance that you hit A before you hit minus B?
Okay, B by A by plus B.
Yeah.
But that's not good.
Yeah. So you hope in a good world that there should be B upon A plus B. And indeed,
That we now show
our
the
world is good.
stopping time.
Hmm?
I cannot do this using stopping time.
Yeah,
But
yeah. That's right. Very cheaply.
Oh,
Yeah, so we are beginning to see the power of martingales. Some results are just very easily obtained. Oh, sorry, this is. All right. So S min tau is a martingale. Okay. We just show that stop process is a martingale. S min tau converges to S tau as n goes to infinity. Everybody with me on this? I want just kind of everyone to appreciate the nuance of this. When will Sn min tau converge to S tau as n goes to infinity? When will this not happen?
Whenever.
When tau is infinity. If tau was indeed infinity with positive probability, then I cannot say that this happens almost surely. Yeah, go ahead.
Can you show the definition of problem?
Well, this is the definition here. And why it's a stopping time? Because tau less than or equal to n, this set should belong to Fn. And that we can check. I mean, I'm not going to make it, let's not like write down all the steps for it, but intuitively, if I show you x1 through xn, you know tau is less than or equal to n or not. Okay, so far you with me? So now the question is, for this to work, I need probably that tau less than infinity is equal to 1. So why should the time to hit either A or minus B be less than 1? I mean, probability that the time is finite should be less than 1. Huh?
Otherwise, you're not reading either A or B.
That's right. You're just staying inside. That just doesn't seem right, right? That's not a proof though, I guess. You expect the martingale, the random walk, to eventually kind of go outside of A and minus B, right? Right. So it requires a proof. One simple way can be that, okay, you say to yourself that at any time in steps, if I'm at any state, in steps A plus B, right? With probability, let's say P is the probability of, well, I have probability half now for this random walk to take value -1 and half of probability -1. So with at least this probability, right? I'm sure I've gotten out at least with this probability.
We go right from the bottom to the top.
Yeah,
We cover that.
that's right. From anywhere, I can go either all the way to the top or all the way to the bottom with this probability for sure. Right? So my probability that my tau is greater than or equal to n times A plus B. Let's make this less menacing. Let's call this Q is less than or equal to Q to the power n.
And this goes to zero.
Right? The fact that even after n times A plus B steps, I've not stopped. Because, in the first set of A plus B steps, I would have stopped with probability Q for sure. Right? The probability that I did not stop in first A plus B sets is less than or equal to Q. Is that clear? That in first A plus B steps, I did not stop. It's less than or equal to Q with probability Q of. Am I saying it correctly? I'm saying 1 minus Q, I guess, yeah. Right? With this probability 1 minus Q for sure, I should have stopped. Right, in 1. And if I didn't do it in first A plus B steps, then in the next A plus B steps, I should have stopped. Right? At least with probability 1 minus Q.
Why 1 minus?
With probability Q for sure, I would stop. With at least Q.
With probability Q, I'll either hit A or minus B. Probability.
I think if we just take probability tau.
I mean, probability that I would have hit is at least Q, right? That you agree, yeah.
Within A plus B.
So I must have stopped in A plus B steps with at least probability Q. There will be more than this. So the probability that I did not stop is at most 1 minus Q. Right? That I did not stop in 2 times A plus B steps is at most 1 minus Q to the power square. So at most is the word I'm looking for.
We can just make this argument simpler, like P tau is greater than equal to n is equal to, is less than equal to 1/2 to the power n.
Hmm?
We can just write P tau is greater than equal to x, is less than equal to 1/2 all of that to the power n. It's 1/2 to the power.
How would you show that?
I mean, P tau is greater than equal to n. So what does this mean? That is not hit n right now, right?
It's not hit A or B.
It's not hit.
Either A or B.
Okay, tau is defined as A or B. Okay.
Yeah, that's That's why we're just counting everything after A plus B steps. First A plus B steps, must have stopped, at least with probability Q. So I didn't stop with at most probability 1 minus Q. In two such blocks, I must have stopped with probability. I didn't stop with 1 minus Q.
Like, when you're saying that with probability 1/2 for A plus B, I must have stopped. That is, the radius is that you moved in one direction.
That's one path, right? I mean, I just have to identify paths on which I would have stopped.
Yeah.
Let's look at the path where I moved in one direction. That gives me some probability. Overall probability of stopping is at least that much. It's that and much more. So probability of not stopping is at most that much. It's actually less than that. So this is true. And now letting n go to infinity, I get that probably that tau less than infinity is equal to 1. Okay. So it's a straightforward argument. You can't stay in there forever because there's always a positive chance that in some steps you leave. And if there's a positive chance after some steps you leave, then if you're going to infinity, this geometric experiment repeats itself. That geometric random variables are finite with probability 1. Okay. So now I have this. So how do I use this result?
Expectation of Sn is equal to expectation of S0 for all n. So expectation of S tau is equal to expectation of S0, which is 0.
Which is 0. That's right. So advise the expectation of S min, the stop process, S of n min tau.
That was just some S tau only, like if you're saying S n is equal to expectation of S0, that also means expectation of S tau is equal to expectation of S0.
Requires a proof.
Wait. We're saying expectation of Sn is equal to expectation of S0. So in general, when you place an actual number by a random variable that takes us.
It requires, I've not shown you so far. That has not been shown so far that S stopped at random time has same expectation as S stopped at fixed time.
Okay.
But what I have showed you is that this process here is a martingale. So expected value of S n min tau is equal to 0 for all n. Because it's a martingale with respect to Fn, this expectation is just expectation of S of 0 min tau, which is just expectation of S0, which is 0. So this I know, but I know that this is true. Why do I know this? Just ignore that you've seen this. Why is the expected value of Sn min tau converging to E of S of tau?
You guys finite increasing.
It's not increasing. It's not increasing.
Dominated.
Dominated, right?
That's what it is. Because these guys dominated by maps AB.
That's so. The word for this is bounded convergence theorem. I mean, when you dominate by a constant quantity.
So it's a special case.
It's a special case of DC. Yeah.
Because you're bounded below by minus me and.
That's right. That's right. Yeah. Yeah, we need to go, right? So E of S tau is equal to 0, right? What's my alarm? I should get up now. Okay. Maybe after 10 minutes. All right, guys. So then you can evaluate this. It's A times probability that S tau is equal to A minus B times probability that S tau is equal to minus B. Right? This is equal to 0. And probability S tau is equal to minus B is just 1 minus probability that S tau is equal to A. Only two events can happen.
Because the.
That's E of S tau, right? S tau can take only two values,
Oh.
random variable. It takes
It
either value A or value B, right? And now you just simplify this and you conclude that probability of S tau is B upon A plus B. Okay. Okay, next time you'll actually show that E of tau it can also be evaluated, expected time to stop. So it's a fairly simple calculation, right, to do this here. That's the beauty of it, that you can do many simple calculations quite easily. We'll revisit this when we start next time. All right.
I think there are two unknowns in that.
No, just one unknown.
Here, that is from, that takes the value A.
And this is with the two probabilities sum to one. Two probabilities sum to one. All right, Vedant, I'll say you buy in both the places.